In this tutorial, we're going to be looking at area under a curve as part of applications of integral calculus. In the last tutorial, we looked at one of the applications of differential calculus, which is increasing and decreasing functions. But for this tutorial, we're going to move into integral calculus. We are going to be looking at area under a curve. So I'm assuming that before this tutorial, you already understand the concept of integral calculus. So that will be the only prerequisite to this class. So if you understand integral calculus as little as finding the integral of 2x dx, you should be able to follow along this class perfectly. So let's start looking at area under a curve. To understand fully the concept of area under a curve, we are going to be considering the Cartesian plane, where I have the x-axis and we have the y-axis and the x-axis. So this is the x-axis, and this is the y-axis. So if you are given a curve y equal to f of x, say this curve, and wish to find the area bounded by this curve and the ordinates x equal to a and x equal to b. So if you are also given that you have a point on the x-axis as point a, another point on the x-axis as point b, and we should find the area bounded by the curve point A and point B. So basically, what we are trying to do is to find the area bounded by this shape, the curve point A and the x-axis. Recall that in mathematics, if you have a definite shape, for example a rectangle, and we have to find the area of this rectangle, we know that the area of a rectangle equal to the length multiplied by the breadth. So if you have A and we have B, so simply we have the area of this shape to be equal to A times B. But in this case, the shape we are looking at, we can't call it a rectangle, a trapezium, or a square. So it's an indefinite shape. So we are going to use integral calculus to find the area of this curve. So to start with, if you take a point, a fixed point h on the curve, just take any random point, say h on this curve, and I extend this to the x-axis. So if this is point O and I name this point E. So if you are given that OE is x and EH to be equal to y, so I have OE to be x, the length of O to E is x, and the length of E to H is y. And also we should take any neighboring points, any points around H. We can take another point A. So we are going to see later when we start looking at the concept of trapezoidal rule that the smaller these 2 points are to each other, the better our estimate. So if you take another point, say B on the curve, and we extend this downward. So if you have that this is x from point O to E as x, a little change from the line EH to the line, if this is D, DB. So this we have a little change, so there's a little change in x over A. And also the same thing applicable at this top. So we know that EH is y, so we also have another YA. So the length of this is the same as the length of EH, and this is y. And over here we have a little change in YA. So from this point to this point, so if you can call this change in y. So we know that excuse me, there's a little change between point E and point D. So we can say that, so we know that EH OE equal to x, and also EH equal to y. So we can say that OD, which is from this point all the way to this point, is simply x plus dx. So you have this to be equal to x plus change in x. The same thing applicable to db. So we're going to have db to equal to, so this is length y plus a little change in y, which is y plus dy. So take note of what we have here. We have points E, H, B, D, and we are trying to look for the length of OE and also OD, EH and DH. So I'm going to recap this again. So we have the length from O to E to be equal to x, and there's a little change between the point E and point D, so denoted as change in x dx. So if you are trying to find the length of point O to point D, we simply add this length and this length. So that's why we have x plus dx. The same thing applicable to the y-axis. So we have point E to point H to be equal to y, and the same thing here, point D to point this is also equal to y, and we have a little change between this point and this point over here as dy. So to find the length of the whole line, db is going to be y plus dy. So here I have db to be equal to y plus dy. So for the sake of this class and for easy understanding, we are going to try to complete this rectangle. So if I will try to draw a vertical line to complete this rectangle. So we have a line A, and we have this completed. So we now have something like a rectangle, and if you give this point F, so we now have this point to be point F. So basically the area we are trying to look for is this area A. So just a small segment of this curve. So if you denote the area which is the area of the shaded part that we are looking for as A. So we are looking for the area of the shaded part, and we call the area to be equal to A. And we denote the element of the area of EHBD. So we have point E, H, B, D. So if you denote the area of E, H, B, D by changing A, so we denote the area of this part E to H to B, which is the topmost part of the curve, and D by change in A. So note that if you look back at this graph, we are trying to find the area of the shaded part, and you should know that from looking at it, the area we are looking for lies in between E, H, B, D. So if you call this part as, if you denote this point as C, so the area we're looking for lies between E, H, C, D and E, F, B, D. Take note. So we are trying to look for area which lies in between E, H, C, D and E, F, B, D. If you look back at the graph, so this is point E, H, C, D, and between the points E, F, B, D. So we are trying to look for the area of the shaded part. So from this, there are some things that we can conclude. So we can conclude that the area of EHCD. So if you look back, we have this to be EHCD, EHCD. So this is a rectangle with the length of y and the breadth of change in x. So you can say that the area of EHCD equal to y dx. So EHCD. So it's a rectangle, so we have the area to be equal to y changing x. And also the area of EFBD. So if you go back, we have this particular rectangle to be EFBD. Let me use white. Okay. This EFBD. So this is another rectangle, and we are going to have the length. So if you look here, the length of this rectangle is y. So it starts from here and it ends here. And from the beginning, we know that this is y plus change in y. So the length is going to be y plus change in y. And the same thing, the breadth is dx. So we have the area of EHCD to be equal to y dx, and the area of EFBD to be y plus dy changing x. So if you're able to note this, there are some things that we can conclude. So we can conclude that y changing x is less than the area of what we are looking for, changing a, and this is less than the area of the bigger rectangle, which is y plus dy dx. So what we are trying to say is that the area of this EHCD is less than the area of what we are looking for, which is the area bounded by this shaded part, and this is also less than the area of the big rectangle, which is EFBD. So that's what I'm trying to write down here. So y dx is less than dA is less than y plus dy dx. And from the graph, we know that change in x is greater than 0. So it's a significant number. So we know that change in x is greater than 0. So if you divide all through by changing x, we're going to have y dx divided by dx less than dA over dx less than y plus dy dx over dx. So we're going to have dx cancel out at the extreme ends. So we are now left with y is less than dA over dx, and this is less than y plus dy. So from here, we know that as dx tends to 0, dy also tends to 0. Let me go back to the graph. So this is dx. As dx tends to 0, meaning that as we shift this particular line db, as we shift it to the left hand side, so dx tends to 0, also dy begin to shift, and also dy is going to tend to 0. So we can also write that as dx tends to 0, change in y also tends to 0. So from here we can write that the limit of as dx tends to 0, so meaning that if you are equating this to be equal to 0, so we are turning dy to be 0 and also dx to be 0. So we are still going to have dA over dx equal to y. So it can either be, since this guy is turning to 0, so it can either be this y or this y. We know that dA over dx equal to y. And recall from differential calculus that we can say, let me change this. Okay. From the differential calculus, we can say that dA over dx is represented as change in a over change in x. So the same thing I'm going to write here, the limit of dA over dx as dx tends to 0, so is equal to dA over dx. So we know this from first principle. So hence we can say that, so if you recall from here, so we have that the limit as of dA over dx equal to y. So if I change this back to y, I'm going to have the limit of dA over dx or better still, so I'm going to have this to be my y, since I know that limit of dA over dx equal to y. So I'm just changing dA, changing a over changing x to be equal to y. So I now have that changing a over changing x equal to y. And don't forget, from our curve, we have that y equal to f of x. So we can say dA over dx equal to f of x. And from where we are going to, if cross multiply, we are going to have dA equal to f of x dx. And don't forget, the area we're looking for is a. So to find a in this case, we call from integral calculus that to find a, we simply take the integral of both sides. So we're going to have the integral of dA equal to the integral of f of x dx. And yeah, so integral of dA equal to a. So leaving this like this, I'm going to have the integral of f of x dx. So trying to find the answer to this, I'm going to have a equal to, so let's say the answer is a function of capital F plus c plus the constant of integration. And this will be the area of the little section of the curve that we are trying to find. So this will be the area of the shaded part of this curve. So this is the area of this little part of this curve. But recall that from the graph, we are trying to find the area bounded by this whole curve, with point B as the upper limit and point A as the lower part of the curve. So if you have this, we can then rewrite our answer in this form. So we're going to have the big area now to be equal to the f of b, which is the upper limit, minus the f of a. So whatever we have this to be will be the area of the whole area under the curve. And in mathematics, we denote this by writing the integral of b to a of f of x dx plus c. So this is called definite integral of the function f of x. So where a is refers to as the lower limit and b is refers to as the upper limit. So a is referred to as lower limit and b is referred to as the upper limit. So this is how we can generalize and find the formula for finding the area under a curve. So let me write that. So basically, if you are looking for area under a curve, we simply have our formula area to be equal to the integral of the lower limit a to the upper limit b of the function f of x dx plus c, which is the constant of integration. So most of the time I don't need c. So and this is the formula for finding the area under a curve. So let's look at two different examples to illustrate this point. For the first example, we have the question, the integral from 1 to 3 of 3x squared dx, and we have to estimate this. So as I mentioned, these are called definite integrals because they have a bounding point. So this is the lower limit 1 and we have the upper limit to be equal to 3. So these are generally called definite integrals. So how do we go about solving definite integrals? So to better illustrate it, is simply looking for the area bounded by the curve f equal to 3x square. So the lower limit in this case is 1 and the upper limit is 3. So that's what this question means basically. So what is simply need to do is to find the integral of 3x squared dx. So the integral of from 3 to 1 of 3 s squared dx equal to, just like we used to find the integral of functions, so you're going to have the integral of 3x squared is 3x cube over 3 plus c. So we're going to be enclosing this in two slashes. So we put the lower limit at the bottom side, this is 1, and the top right hand corner we have the upper limit 3. So 3 is going to cancel out, and I have s cube plus c 1 to 3. So what we need to do to solve this is to firstly substitute 3 into this expression and subtract it, and subtract another expression after we substitute 1. So the first thing is to substitute 3. So we're going to have 3 cube plus c minus, then we substitute 1. So 1 cube plus c. So here I'm going to have 27 plus c minus 1 minus c. So c is going to cancel out. Always c will be cancelling out. So if you recall from normal integration, so you're going to be having c all the time, but in this case c will always be cancelled out. That's why they call it definite integrals. You know the definite answers, no more constant c. So we know that c is going to cancel out. So 27 minus 1 is going to be 26. So I have the area bounded by the curve f of x equal to 3x squared with lower limit of 1 and the upper limit of 3. So let's look at another example. In example 2, if you have to find the area bounded by the curve y equal to x squared and the lower limit x equal to 1 and upper limit x equal to 2, and we have to find the area bounded by this curve y equal to x squared, x equal to 1, x equal to 2, and the x-axis. So to better illustrate this, let's try to draw the graph of y equal to x squared. We know that this is a quadratic graph and the coefficient of x squared is positive, so we are going to have a cup-like structure. So if I have this to be 0.1 and I have this to be 0.2. So basically, what we're looking for is the area bounded by this curve. So just like we did in the previous example, so we're going to have the area to be equal to the integral, the lower limit is 1 and the upper limit is 2. So and we have our f of x to be equal to x squared dx. So here the first thing we have to do is to find the integral of x squared. So area equal to the integral of x squared is x cube over 3. Again, we have the lower limit and the upper limit. So first we substitute the upper limit and then we subtract it from substituting the lower limit. So area equal to 2 to the power of 3 plus c over 3 minus 1 to the power of 3 over 3 plus c. So I'm going to have the area to be equal to 2 to the power of 3 is 8, so we have 8 over 3a plus c minus 1 over 3 minus c. So again, c is going to cancel out, and I have 8 over 3 minus 1 over 3, and then I have 7 over 3 square units as the area bounded by the curve y equal to x squared, x equal to 1, x equal to 2, and the x-axis. So this is a little intuition of what it entails to find the area under a curve. So this is a very quick introduction to finding the area under a curve. There is still more to this topic and more is to come later in this tutorial. So something that we have to take note is that most time while finding the area under a curve, we're trying to estimate the area under the curve. So when we start looking at trapezoidal rule, we're going to see that the smaller, we're going to be looking at a variable h called the width. So when we start looking at trapezoidal, we're going to see what we call width. So we're going to see that the smaller the width, the better the estimate is going to be. So the smaller the width, the better the estimate. So that's basically how the application of integration works when considering the area of finding the area under the curve. So that's basically it for this tutorial, and thanks for watching. If you find it useful, don't forget to like, give it a thumbs up, and before you go, subscribe to this channel. It means a lot to me. So thank you, and I'm going to see you in the next tutorial.